I am Doug Masterson. I'm the Senior Associate Provost here at the university, and I'm also an organic chemist. And so Dr. Hayhurst had to be out of town today, and he asked that if I would come and teach the Friday class for him, and I said sure. And so here I am. Can everybody hear me okay? I don't use a microphone. I do have a microphone attached to me. I'm capturing my lecture for today, and I'll put it on my YouTube channel. I'll give Dr. Hayhurst the link so you all can go to it. So whatever you see on the screen up there, you really don't need to worry about taking notes about. It'll be in the video. And so focus more about what we do on the board. And so Dr. Hayhurst gave me a series of slides to go over, and I looked at those, and I thought that maybe it would be a good idea if we kind of take a step back just so that I know where you all are. And I thought maybe we would start off by working a few problems together. And so maybe we'll spend maybe 10 minutes or so on that. And so I've got two problems up here. I've got the top problem is taking an alcohol, treating it with sulfuric acid, and getting the alkene that you see there. The bottom problem is taking a primary alkyl bromide, and DBU, I looked through the slides, you haven't been introduced to that. All you need to know is DBU is a bulky non-nucleophilic base. Okay, so just think of it as a base. Okay? And it's undergoing a reaction to give an alkene. So why don't you pair up with your neighbor and work through these two problems to see how this happens. So think about a mechanism that would give the products that you see there, and then we'll come back together and we'll work through them on the board, okay? So take 2-3 minutes. You can discuss among yourselves, your neighbors. Hey, how are you? It's the end of the week. That's good. How does that go to that? Yeah, so think about the mechanism. With the H2SO4, yeah. So if we take that alcohol, sulfuric acid, how do we get that product? If we take that alkyl bromide, that a base, just think of it as a base, how do we get that alkene?
So you want us to like draw out the mechanism?
Yep. Think about how that happens. Yeah, that's a mechanistic question. Yep. Okay, let's come back together. In general, what kind of reactions are these? If you had to give them a category, what is the reaction type? These are elimination reactions. We are eliminating something from the molecule. What are we eliminating from the molecule, the starting material in the first example? OH and what else? H. And H and OH combine to make what? Water. So this is called a dehydration. Okay? If you've ever seen the video where they take sugar and they pour sulfuric acid on it and it comes out of the beaker as this big black blob thing, right? That's a dehydration. That's what's going on. That's what we're doing here. We're taking this alcohol, we're reacting it with sulfuric acid, and we're going to get a dehydration. We're going to eliminate water from the molecule to give us an alkene. Is that all that's happening, however? What else is happening? The structure is changing. And when the structure changes, what do we call that? A rearrangement, right? So this is a carbocation rearrangement mechanism, and we'll talk about that in a moment. So, and since I kind of gave it away that there's going to be a carbocation, what kind of elimination mechanism is this? You know of two right now. You know of E1 and E2. Which one is it? Better be careful, I might pull up the wrong finger. 1 or 2? It is an E1 mechanism, right? E1 mechanisms go through carbocation intermediates. So you're going to have some type of carbocation intermediate. I'm just going to put that there, right? What else do you know about carbocations? Are they stable? Why aren't they stable? They have an empty p orbital. They don't satisfy the octet rule, right? It's a carbon atom with 3 things bound to it, an empty p orbital. And how many electrons does it have? It's got 6 electrons around it, right? I heard the word 6, the number 6. Okay? What do we know about carbon? It likes to have 8 electrons. It likes to satisfy the octet rule, right? But carbon's on a special place on the periodic table, and what happened to the periodic table in this room? Okay, anyway, if you look on the periodic table, carbon is in a special place on the periodic table where it likes to have 8 electrons, but it can actually have fewer electrons, okay? It can have 6 electrons. It can actually have 7 electrons. It cannot have, however, 9, 10, or 11, or 12, but it can have fewer than 8. But when it has fewer than 8, it's highly reactive. And so there is a rule that I always say about carbocations. And it's not in your book, but it is, I call it the cardinal rule of carbocations. And the cardinal rule is, anytime you generate a carbocation, you need to stop, pause, and think about it, and ask yourself, can that carbocation rearrange to a more stable carbocation? Because if the answer to that question is yes, then do it. And you will rarely hear that from a chemist that definitively. If a carbocation can rearrange to a more stable carbocation, do it. That's going to be 99.9% of the time the correct way to go. Okay? So let's think about this. Let's think about this particular problem. Okay? What's happening with the sulfuric acid? Sulfuric acid, I think you all will agree, is a strong acid, right? Strong acids dissociate into H plus and some counter ion. In this case, H plus and HSO4 minus, right? So I like to think of it as just H plus and HSO4 minus. H plus is a what? It's a Lewis what? It's a Lewis acid. And Lewis acids like to react with what? Say it. I heard it. Lewis bases. Where's the Lewis base for it to react with? Pardon? Oh, okay, I want to ask you. What is a Lewis base? It is an electron pair donor. Where do we have on the molecule that has electron pairs? That I haven't drawn them. Yeah, the oxygen on the OH. There's a pair of electrons there. This is nothing more than a simple Lewis acid-Lewis base reaction. The OH electron pair becomes protonated. Okay? And so I'm going to erase the product here, and I'm going to draw the intermediate. This is a reversible reaction. I can draw squares pretty good. Not too bad. OH2. What's going to be the charge on the oxygen now? Positive, right? So we've got a positively charged oxygen. We also have a counterion. We got to keep everything balanced. Keep me honest with that. Sometimes I let the counterion just go away and I forget about it, but know that it's there all the time, right? We have to have charge balance. What do we know about an oxygen atom that's positively charged? Is it happy or not? Not happy at all. Why is it not happy? It's very electronegative. It wants electrons towards it. It doesn't want positive charges towards it, right? So what's it going to do? It could do that, and when it does that, it just goes back to the starting material. And that's why we have a reversible arrow. That is definitely something that can happen, but does that get us to the product? It does not. So that is an uneventful event, okay? It just goes back to starting material. We can't tell that anything ever happened. But sometimes what happens? Where else can it get electrons? It can get them from a bond, right? And so it can actually just go ahead and steal the electrons between this oxygen-carbon bond, and those electrons will go on to oxygen. Plus water, plus HSO4 minus. Okay. What have I just generated? Water, and what else? A carbocation, right? Is that carbocation stable? Not really. What kind of carbocation is it? It is a secondary carbocation. So what do you all remember about carbocations? We remember that we can generate secondary, but they're less stable than tertiary, right? What about primary? They're extremely unstable. So we almost always say, oh, don't do that, right? But secondary is okay, tertiary is even better. Anytime you generate a secondary carbocation on any exam that you ever do, you stop and ask yourself, can that rearrange to a more stable carbocation? If the answer to that question is yes, do it. So how can cations rearrange? Two general ways that you've learned. You can have alkyl shifts, which can also include a ring expansion, which obviously is the answer here, right? Or you can shift hydrogens, right? So, anytime you have a carbocation, I also like to number my carbons so we know what we're all talking about. So, and you can number them any way you want. I always just number to give the carbocation the lowest number possible. And so that's how I've numbered it. What has to happen here to get to that product? I've got a 4-membered ring in that intermediate right now, but what's the product, the final product? A 5-membered ring. So what has to move? We have to move one of the carbon-carbon bonds in the 4-membered ring and move it over one position, which would make a 5-membered ring, right? So does it matter if I pick on the 3,4 bond or the 3,6 bond? Doesn't matter at all because they're equivalent. They're the same thing. And so I'm going to just move the 3,4 bond to carbon number 2. So this arrow is telling me that I'm taking the electrons from the bond between carbons 3 and 4, and I'm going to move those electrons to carbon 2. And in doing so, what happens to carbon 4? What is it now bound to? It's going to be bound to carbon number 2. So those electrons are taking carbon number 4 with it to bind to carbon number 2, and carbon number 3 is going to be missing some electrons, so it's going to be the new cation. Okay? So that's how we do that. I always indicate a rearrangement using a little curlicue arrow. So that's kind of a rearrangement. Okay? And so we're going to have now a 5-membered ring. We're going to have a methyl group that sticks off of that. So that's going to be carbon number 1. There's carbon number 2. There's carbon number 4, 5, 6, and 3. And 3 becomes the new what? Carbocation. So I'll just put a positive charge out there, right? Now, what kind of carbocation is that? Is that primary, secondary, or tertiary? It's a secondary too. Can that rearrange? Actually, it can. Doesn't really matter in this case, because whether or not it rearranges, you get the same product. How would that rearrange, though? What would have to move? Notice I've already got the final shape, if you will. But if this hydrogen shifts to here, I would then end up with a tertiary carbocation, which then would eliminate and give the product. But really what happens, as far as I'm concerned right now, this hydrogen that's on carbon number 2 gets plucked off, and you form the product. And I'm not going to renumber, but you can see that that's how that works. There's another possibility here, though, right? That's obviously what had to happen because that gives you the product. But many of you should have asked, well, now wait a second. Why couldn't that hydrogen have shifted here and just given me a tertiary carbocation? Isn't a tertiary carbocation more stable than a secondary? It absolutely is, right? So why did this not happen? Where the hydrogen here migrated here to give you the tertiary carbocation on that carbon. Can anybody answer why that is not the case? What's the hybridization of a carbocation? You're talking about the shape, and I'll get to that. But what's the hybridization? Not sp3, but sp2. It is sp2. And its shape is trigonal planar, right? Would look something like this. So I've just used a red and a blue stick to be the 2 lobes of the p orbital that is empty. And then here are the 3 bonds to that carbon. So this is a carbocation. Notice around the carbon it is trigonal planar, right? What's the bond angles between something? If you have in a plane and you've got 3 things, what has to be the bond angles? 120, right? Because a circle gives us 360. 360 divided by 3 is 120, right? What's the bond angle in a box? 90 degrees. So even though that's a tertiary carbocation, is that a stable carbocation? No, because it's taking these and trying to squish it into 90 degrees, and it doesn't like that at all. That's why it goes from a secondary to a secondary. That secondary is more stable because we have relieved ring strain. That box has 90-degree bond angles. Those carbons are sp3 hybridized. They want to have a 109.5-degree bond angle, but a box is 90. So it can move one of those bonds, relieve some of that ring strain. Yes, you get another secondary carbocation, but overall the molecule is more stable. Okay? So carbocations will rearrange to more stable carbocations if they can do so. Okay? Does that make sense? All right. How about the bottom one? Why in the bottom case am I not getting the same product? Is the mechanism the same? No. Anytime you take 2 substrates that are different and you get to the same product, 98% of the time it's because it went through the same mechanism. Here we have 2 different products, so the mechanism can't be the same. So if the top one was an E1 mechanism, what do you think the bottom one is? It is an E2 mechanism, right? E2, what does that mean? Or what does it not mean? No carbocation. And if we don't have a carbocation, are we going to get rearrangements? Nope. No rearrangements. Okay? And so in an E2 reaction, the base reacts with a beta hydrogen and eliminates HBr. Pretty straightforward, right? What do we know about E2 reactions beyond that? So let me cheat a little bit here and not have to redraw everything. Right, so we're just going to call DBU a base. Bases have electron pairs, right? So how does this reaction work? If it's E2, how does it work? In fact, let me draw it like this just to be a little more clear. And I'm only drawing one hydrogen for convenience. How does this happen? Does the bromine leave first? If the bromine left first, we'd get a primary carbocation. Is that good? No. You were saying? Okay, yeah, we're going to go through a transition state. Yep, that's good. And how's that going to look in words? What does the base have to react with? Okay, so how do I do that? How would I push those electrons? I like that. Yep. Double-headed arrow, I'm moving a pair of electrons from the base to the hydrogen. Hydrogen can only have one bond, though, so what happens to its carbon-hydrogen bond? Are the electrons there? What happens to those electrons? Gives it to the Br? Almost. What are those electrons going to become? They're going to become a bond. What kind of bond? The double bond, right? So those electrons are going to move here. Carbon can only have 4 bonds. I can't have 5, so what has to happen? Now the bromine leaves, right? It is concerted in the transition state. All this is happening at one time. You'll notice that I purposely drew the hydrogen and the bromine being what with respect to one another? Opposite. What's another word for that? Trans. Sometimes we call that anti-periplanar or anti-coplanar. You'll hear a lot of terms for it, but the bromine and the hydrogen have to be opposite to one another. That is absolutely the fundamental thing, right? Do you all know why that has to be the case in an E2 reaction? Other than the fact that the book told you so? There is a steric issue, right? If we try to put that in there, that would be kind of problematic. What does bromine have around it that I didn't draw? They have electrons, right? And electrons like to be around electrons. Is that right or wrong? That's wrong. Electron pairs like to repel one another, right? So if the hydrogen and the bromine were on the same side, and the base started to come in and react, those two the electron pairs from the base and the electron pairs from the bromine would get close to one another, right? That stinks. So that's no good. So there is a steric kind of argument, but it's really an electronic argument. And also, these electrons have to come in and form the bond and kick out the bromine. Have you all already talked about substitution reactions? Yeah. So this is kind of like a nucleophile coming in from the backside and kicking out the leaving group, which would be kind of like a what? An SN2 type mechanism. So the electrons are the nucleophile. They've got to come in from the backside and kick out the bromine. Okay? And so that's why that works the way that it does. And since this reaction has no carbocation intermediate, all we can form is the double bond that you see there. We don't get any rearrangement. Okay? I said we were only going to take about 10 minutes and we're already over that. But, oh well. That's good. Let's try this one. So take a minute or two. What kind of reactions are these? These, again, are elimination reactions. Now, whether or not it's an E1 or an E2, we're going to debate about here in just a moment. Okay? Do the two starting materials, the alcohol and the bromide, look similar? They do look very similar, right? So, I mean, if I build the model, I've got a larger model kit than you all do. I really like working with models. And so if you look at the model, what you'll see is the methyl group coming out of the plane of the board towards me. You see this red stick, which is either going to be the OH or the bromine going away from me. So the methyl group and this group here are trans to one another, right? We know that. And so they do look very similar, right? But one happens to be an alcohol and one happens to be an alkyl or a bromine or bromide, right? Anytime, another piece of advice for you, anytime you have an alcohol and you have a strong acid, something like sulfuric acid, phosphoric acid, HCl, HBr, protonate the alcohol. That's the first thing you do. You get the Lewis acid, Lewis base reaction where the OH reacts with the acid and gives you a protonated alcohol. That then gives you, right, OH2 plus. Does it like to be OH2 plus? Does not. And so what happens? It'll leave, right? And we'll get a carbocation, right? So we have a situation where we've got this. This leaves. We end up with a carbocation. What kind of carbocation is that? That's secondary. That is a secondary carbocation. Right? So that would be, so this is left. My little red stick here, right? It is now a carbocation, so I'll put the carbocation carbon in there. Give it the right shape. So there's the carbocation. We know that big groups like to be equatorial, right? Right? So is that going to be the most stable carbocation that we can have? What can move? This hydrogen can move, can't it? So this hydrogen can move from here to here and put the carbocation there, and it would go from a secondary carbocation to a tertiary carbocation, right? So we're going to call that a rearrangement. This happens to be a hydride shift. And now what happens? And I've taken a few shortcuts, I apologize. All right, we've got HSO4 out here. And now one of these hydrogens, either one of these hydrogens or one of these hydrogens, gets removed, and we end up with the product. Okay? Why am I not eliminating a hydrogen from the methyl group? Aren't there more hydrogens there? Pardon? Okay, what is it? The methyl group is stable. The product is stable. What do we know about the stability of alkenes? The more substituents around an alkene, the more stable, right? And so if I remove one of the hydrogens from a carbon that has fewer hydrogens, I get the more substituted alkene. Whose rule is that? Starts with a Z. Zaitsev's rule. Zaitsev's rule says that the carbon with the fewest hydrogens loses the hydrogen, right? Kind of sounds not fair, but that's the way life is sometimes, right? And so you eliminate and you get the product. What's happening in the bottom example? Yes, sir. Okay. So which part are you talking about? Are you talking about where I generated the tertiary carbocation?
Right. And how that group.
So when I generated the tertiary carbocation, what's the geometry around the carbon? Trigonal planar. And so I drew all three groups to that carbon in the plane of the board. That make sense? And that's why it went from coming out to now being flat. So that's obviously a E1 mechanism. We go through a carbocation, right? The bottom one, wait a second. Now I'm using sodium ethoxide, which is a base, and I'm in ethanol, right? So I no longer have acidic conditions, I have basic conditions. So what kind of mechanism do you think this is going to be? This is going to be an E2 mechanism. Now Zaitsev's rule told me that the carbon atom, beta to the leaving group, right? So there's my leaving group. So there's the alpha carbon. There's a beta carbon there, and there's a beta carbon there. Zaitsev's rule told me that the carbon atom with the fewest hydrogens loses the hydrogen, which meant that it should be this carbon that's losing the hydrogen to give us exactly the same product. But obviously that's not the case. Zaitsev's rule sometimes lies to you. What do we know about E2 mechanisms? The hydrogen and the bromine have to be what with respect to one another? Trans, right? So here I've got the model. I've got the methyl group. I've got the bromine, right? Is the methyl group going to be pointing straight up and being axial? Or is it going to prefer to be equatorial? Equatorial. Big groups like to be equatorial, right? So now when I look at this hydrogen and I look at this bromine, are they trans to one another? They are not. So this hydrogen is never trans to that leaving group. However, when I look at this bond, right, I notice that the bromine and the hydrogen here, they're not trans either. Is this hydrogen and this bromine trans? They are not. They are not. But when I put it in this conformation, which it doesn't like to be in, but it will be in there by maybe 1% of the time, now what can you see? There's the bromine and there's the hydrogen, and they are trans to one another. So it is actually the minor conformation that is responsible for the generation of the product. These are in equilibrium. They flip back and forth all the time, right? And when it's like this, the reaction can happen, right? and then that's what drives the reaction, okay? So sometimes it is not the major conformation that is responsible for the chemistry that we see. Okay, I got to actually get to some real stuff today. So, I hope you all found that helpful. And you are more than welcome to go to my YouTube channel anytime and look at the videos from the past years. I'm not teaching this year, which is kind of a bummer, but let's go ahead and move on. So, let's talk a little bit about the acidity of terminal alkynes. What is an alkyne? A carbon-carbon triple bond, right? This is one of the most useful organic functional groups that are out there, okay? And so it turns out that these hydrogens on the carbon-carbon triple bond are actually fairly acidic, okay? Why? Why might they be more acidic than a typical carbon-carbon or carbon-hydrogen bond, excuse me? That is a true statement, but it doesn't explain why. That is a decent hypothesis, but not the answer. And that's okay. That's okay. So in chapter 3 or chapter 4, wherever, you talked about the acidity of compounds, right? And there were some effects. And one of those effects was the hybridization effect. What's the hybridization of a carbon atom? sp. What does sp really mean? It means that it's one part s character, one part p character. An s orbital is like a sphere, right? And the electrons can get really close to the nucleus. If you're in an sp3 orbital, you're actually in an orbital that looks more like a p orbital, and p orbitals never let electrons near the nucleus. Well, if you're a pair of electrons, would you rather be near something that's negatively charged or near something that's positively charged? Positively. Because you all learned as kids, right, that opposites attract, right? Like two opposite sides of a magnet. Same kind of thing here. So the closer that those electrons can get to the nucleus, the more acidic the protons. And so you really should have these rough ranges memorized. pKa explains 99% of all organic chemistry. It really is nothing more than a Lewis acid, Lewis base interaction 99% of the time. Okay, and so we notice that the hydrogen here is about a pK of about 25. Would you all consider that a strong acid? Absolutely not, but to an organic chemist, it is a strong acid, because most of what we deal with are sp3 hybridized carbon-hydrogen bonds, and they have a pK of 50. So 25, we can do stuff with that. We can treat that as an acid. I've got bases in my lab that will sit there and just pull that hydrogen off pretty easily. Okay? Not the simple bases that like sodium hydroxide or anything, but we do have bases that are strong enough to pull off those hydrogens. And so that so-called acetylenic hydrogen turns out to be quite useful. Okay? And I'm going to skip through some of this stuff, but you really need to kind of have a rough idea for your acids and your bases, especially when you get to organic 2. It's going to be very helpful for you. How many of you are going to take the MCAT? All right, you're going to need to know your acids and bases. I'll let you in on a little dirty secret. Biochemistry is all acid-base chemistry. They just don't call it that. So if you have a good grasp of acids and bases, you can figure out the chemistry that you need to figure out for the MCAT. Okay? So I'm going to skip through some of this. I don't know why we've got all that on there. And let's talk about how we can synthesize alkynes. We've just established that they're useful. Let's talk about how we can make an alkyne. Well, it turns out that you can do what's called a double elimination. Okay? So what do we have here? If we look at this one carbon, we've got an alkyl halide. If we look at this carbon, we have a alkyl halide. Okay? And so these halogens are on adjacent carbons, and we call it a vicinal dihalide. Okay? So if you hear me say vicinal, we mean on adjacent. Okay? So this is a vicinal dihalide. And we've got two molecules of this stuff. What is this stuff? What do you think it is? Is it an acid? Is it a base? Is it a nucleophile? Is it an electrophile? It is a base. And not only is it a base, it's a pretty darn strong base. It's got a pK of around 35-ish. I deal with government numbers all day, so ish works pretty well for me. Okay? And if you have the ish of your numbers, you'll do okay in this class as well. All right? It's the reason I became an organic chemist. I don't have to worry about dealing with things to the decimal point. Okay? So 2 molecules of sodium amide is what we call this. It's a strong base. What do you think it's going to do? It's going to pluck off those hydrogens. It's going to do it twice. It's going to pull off 2 hydrogens. 2 bromines are going to leave, and we're going to end up with a carbon-carbon triple bond. Okay? You typically have to heat this a little bit. You need a really strong base to do this, stronger than just to eliminate to get an alkene. And here's why. Okay? Push the arrows for me. Where are they going to go? Where do I start? Where do they go? Where do we always start in a mechanism? Pardon? Okay, we always start at electron pairs. Always find the Lewis base first. It's a good rule of thumb. Doesn't always work, but it works most of the time. So here's our Lewis base, and it's a strong Lewis base. So I'm going to start at one of these electron pairs, and I'm going to draw what kind of arrow? Double-headed or single-headed? Or, well, you know, a double barb or a single barb. I haven't taught all semester, and I started to lose my language. So double barbed arrow, right? Why are we going to use a double barbed arrow? Because it's a pair. That's right. So I'm going to start here, and I'm going to go to one of the hydrogens. Okay? And that did everything for me. Okay, great. So these electrons now come and form a carbon-carbon double bond, and the bromine leaves. And we end up with this product. That reaction did not require a really strong base to happen. We could have done that reaction with a weaker base, something like potassium butoxide. But we need the really strong base for the next reaction in the step, right? Because now I've got to eliminate this hydrogen and this bromine. The hybridization of these carbons is sp3, and the hybridization of these carbons, sp2. Do we typically think of doing like SN2 chemistry on an sp2 hybridized carbon? We do not, right? It typically doesn't happen. And so to get it to happen, we got to beat the living daylights out of it by using a really strong base. We got to force it to happen, okay? And so that's what the second second molecule of the really strong base does. It's strong enough to pull off a hydrogen off of an sp2 hybridized carbon, and then the elimination occurs, and you end up with the carbon-carbon triple bond. Okay? Pretty convenient. Easy way to make carbon-carbon triple bonds. But you got to have the dihalides for this to happen. Okay? So here's a couple of examples. You can take this dibromide. You can treat it with 2 equivalents of sodium amide. You can get this carbon-carbon triple bond. What would be the name of this molecule? How many carbons do we have? 4. So the parent's going to be a bute. And what's the functional group? It's the carbon-carbon triple bond. And what do we use for that? YNE. So it's going to be a butene. What kind of butene is it going to be? 2-butene. The numbering is important here, right? So we end up with 2-butene. Here's another example where we take a carbon-carbon, or excuse me, a dihalide, react it, and we get a carbon-carbon triple bond. I won't ask you to name that one, okay? Now, if you have a situation where one of these bromines is on the terminal carbon where we've got a lot of hydrogens, you actually need at least 3 equivalents of sodium amide. The reason is that the product that you generate, you will have a carbon, carbon, carbon-carbon triple bond, and then that last carbon has a hydrogen. And that's an acetylenic hydrogen, which is acidic. And so that third equivalent of that sodium amide plucks off the hydrogen, and you end up with what's called acetylide, IDE. Okay? And so now what we have is a carbon atom with a lone pair of electrons and a negative charge. And to get the hydrogen back, we simply take this reaction mixture and dump it into a mild acid. Typically, organic chemists, when we say mild acid, we mean an aqueous solution of ammonium chloride. And so you dump it in there, and you get your acetylenic hydrogen back. Okay? But these types of molecules right here are pretty useful. Can anybody tell me why those molecules would be pretty useful? Why would having a carbon atom with a negative charge on it be useful? Huh? It's willing to bond. We can form bonds with it. I like that. What else can we do with it? Or what else is it? Is it a Lewis acid? Is it a Lewis base? It's a base, right? What else is a Lewis base that's useful? Pardon? Well, okay, that's true. Something else I'm thinking about here, though. Nucleophiles. All nucleophiles are what? Lewis bases. But are all Lewis bases nucleophiles? No. However, acetylides are darn good nucleophiles. Okay? They like to react with other carbon atoms that have leaving groups and make carbon-carbon bonds. By the time you finish organic chemistry sequence, you'll know 98% of everything that I know about organic chemistry. But that 2% that I know that you won't know is pretty dang powerful stuff. Okay? But the problem in organic chemistry isn't making alcohols, it's making carbon-carbon bonds. The reason that we don't have cheap access to drugs is because we don't know how to make carbon-carbon bonds really, really, really efficiently. Mother Nature does. We struggle with it. But acetylides are one of the ways that we have to make carbon-carbon bonds. Okay? So the mechanism here, we'll just go through it pretty quick, right? Second elimination, and you get the carbon-carbon triple bond. Now that acetylenic hydrogen then has to be deprotonated, and you end up with the acetylide anion, which again is useful. And then that just comes back by plucking off the hydrogen from the acid, and you end up with your final product. Okay? How would we name that molecule? That one right there. Not ethylene. Ene would be a double bond. Ethyl? 2 is F. Okay, so it's propyne, right? How come I didn't have to put a number with it? Yeah, numbering doesn't matter. The carbon-carbon triple bond can be here or here. It's the same, you can't, there's no numbering that's relevant here, right? So, we can also make these alkynes by the dehydrohalogenation, which is what we've been doing, of what's called geminal dihalides. Wait a second. The other ones were called what? Vicinal. Now we're talking about geminal. So what's geminal? Gemini, right? What's it mean? For our purposes, it means on the same carbon. So a geminal dihalide has the 2 halogens on the same carbon. So you can take things like, don't worry about this yet, but you just have 2 halogens on the same carbon. We can eliminate, because this methyl group has 3 hydrogens, we can eliminate HCl twice, and we can get to the same product. Okay? All we need are 3 equivalents of sodium amide in this case, and then dump it over some weak acid, and we can end up with a carbon-carbon triple bond and get our acetylide pretty easily. Okay? So, we've just talked about that. I don't know why it's back up there. All right. So, here we have an acetylide, and we have, what's X usually used for? Some type of halogen. So here we have, let's say, or an iodine. Doesn't matter. Okay? Predict for me what that reaction is going to be. I heard SN. SN1 would require what kind of alkyl halide? Primary, secondary, or tertiary? Tertiary. That's not written as a tertiary. That would be written kind of as a primary, right? So what? It's going to be SN2, right? So what's going to happen, right, is the nucleophile is going to attack the carbon. The leaving group's going to leave. That's an SN2 reaction, right? We've just formed what? What does this arrow tell me? A bond between two carbons. There's really only about a half a dozen real ways to make carbon-carbon bonds. You just now know one of them, right? You just did something that people at Merck and Johnson & Johnson struggle with every day. How do we make that carbon-carbon bond that we want to make in our drug, right? And a lot of times they do simple things like this. They take an acetylide, react it with an alkyl halide, and they make a new carbon-carbon bond. That is the power of organic chemistry, the ability to take what Mother Nature has given us in crude oil and convert it into all these things that we use. And the organic chemist's bane is how to make the carbon-carbon bonds. It really is, okay? This works really well for primary alkyl halides or methyl halides, and it completely sucks for tertiary alkyl halides. Because tertiary alkyl halides, do they like to undergo SN2 reactions? Not at all, because the nucleophile can't get to the backside to kick out the leaving group. So if you had a tertiary alkyl halide here, a reaction would occur, but that reaction would actually be an E2 elimination. This would function as a base, not a nucleophile, right? So the structure of the alkyl halide matters an awful lot, okay? So typically you got to have a primary or a methyl. It will work for secondary, but you get a mixture of products, you get a mixture of elimination and a mixture of substitution. Tertiary, it never works to form carbon-carbon bonds for all practical purposes. So let's look at a couple of examples. Keep me on track. So we've got about another 3 minutes. What's going to happen in this first reaction? What is the Lewis acid and what's the Lewis base? Okay, the Lewis base is the sodium amide, NaNH2. So what's the acid? The acetylene, the hydrogen on the acetyletic carbon. It's just a Lewis acid, Lewis base reaction. You actually pull off that hydrogen, you end up with the acetylide and sodium. I've actually done this particular reaction. It's kind of cool, literally, because ammonia you typically think of as a gas, but liquid ammonia, if you cool it down to like -40 or something, you can get it to liquefy. And so when you make, when you put sodium amide in liquid ammonia, it turns this beautiful blue. It is this just, you know, I wish I could paint my vehicle with it. I mean, it's that pretty of a color blue. And you then add in your acid and you get the acetylide. That then reacts with some carbon with a leaving group. Here we're dealing with iodomethane. We do an SN2 reaction and we form the carbon-carbon bond that we want. And if we reacted this with a secondary alkyl halide, we would end up just generating our starting material again, which is kind of a failed effort, and you'd end up with a carbon-carbon double bond. If you came to my lab and proposed to do this kind of chemistry, you'd get fired, okay? Because you're generating cheap materials from an expensive setup. That never works, right? You got to have things that work really well. So you would never want to do an E2 elimination this way. If you really wanted to get this from this, you would use a much cheaper base than the acetylide. You would use something like potassium tert-butoxide or something. Okay? All right. Are there any questions? A couple minutes for any questions about the problems that we worked. I will tell Dr. Hayhurst kind of where we finished off. He will pick back up with that. I will send him the link to the day's screencast. You will not see what was on the board, but you will see what the problems were that we were working as a group. And if you have any questions, feel free to email me. I'd be happy to answer anything that you may have.